Our group created the FireView system. I'm Eric. This is Matt. This is Ryan. Our sponsor was Professor Madumbai. The basis of the project was we created a wireless sensor network to help aid firefighters while fighting wildfires. The basis of how it worked was there was an end node connected to each firefighter. This end node would gather location, temperature, and movement data. This data was then wirelessly transmitted to a coordinator, which was attached to a computer and fed this data into the running application.
The general requirements of our project is that the sensor receiver or the end node and coordinator, for the sensor, it should operate between -30°C and 120°C. From research, we felt that this temperature range was ideal for our project because unless the firefighter was actually submerged in fire, our project would not melt. Also, the transmission and reception of data was from 0 to 1,000 meters. For the computer interface, our application, we wanted to be able to view all the data from each firefighter at once, a menu system to view each individual fighter, and to be able to plot the location of the firefighter on Google Maps. For safety, since it was going into fires, we wanted it to be small enough to not hinder firefighters' movements when it was attached to them. And we also wanted to have a distress signal that would occur after 1 minute if the firefighter was not moving. For the mechanical side, we wanted the enclosure to be durable. It had to withstand a max temperature of 120°C. And it also had to withstand a drop of 4 feet, withstand vibrations, and be water resistant since firefighters use water to put out the fires. On the right, this is an exploded view in Autodesk Inventor of our project showing each main component. The main components was, the first is the Arduino Uno. That was the programming board we used, and all the parts were connected to it. We used the XB Pro 900 RP SMA radio. This is our radio we use for wireless communication. The Adafruit Ultimate GPS. This is our GPS module used to get location data from each fireman. An ADXL335 accelerometer. This was used to track the movement data. A K-type thermocouple. This was used to measure the temperature values. And then a thermocouple amplifier was used to amplify the measurements from the thermocouple so we could use them in our application. For the GPS module we used, it has 2 digital outputs, and the actual module itself is able to collect longitude, latitude, elevation, speed, time, date, and the number of satellites it is connected to. And from not being powered to powered on, it was able to get a fix on its location to correctly transmit the right data at roughly 45 seconds or less. For the accelerometer, most people don't know what an accelerometer is. It's a device that measures acceleration forces, whether that's due to gravity or movement. And for our accelerometer, it had 3 separate outputs, the X, Y, and Z axis, and they are able to measure in ±3 Gs. And we used it to determine if there is a firefighter that is injured. How we use this was we'd be able to track the movement data of each firefighter, and it would send this to our application. And for a firefighter that's moving, the data would constantly be changing since they are moving the acceleration data to be changing all over the place. So if they were, for say, injured and on the ground, unconscious, unmoving, the data would be the same for the entire minute, or roughly the same. And on the application, we'd be able to know this and send a signal.
So for the temperature collection, we decided to use a K-type thermocouple. The reason we didn't use anything that was digital or similar to a previous lab, the temperature sensor, was we needed something that would be able to operate at 120°C as a max temperature, or even higher, possibly. So we decided to use a K-type thermocouple. As you can see, the operating temperature range is well within both our minimum and maximum. And this allowed us to take accurate readings based on the temperature that it was experiencing. To use the thermocouple, we had to use a thermocouple amplifier, which you can see on the right there. It's just a small chip that allows you to get an output for the temperature. And this is the schematic that we used for the thermocouple amplifier. As you can see on pins 1 and 14, which are all the way on the left, you can see that that's where the thermocouple will connect. And based on this hookup, if you look at the last 2 pins on the right side, on the top, you can see that we will get a 10 millivolt per degree Celsius output, and that would be able to be read analog through the Arduino board.
So we chose the XB Pro 900. There are multiple XB radios. We chose this device because it operates on 900 megahertz frequency. This frequency range is ideal for long range applications like this. The actual radio itself on the spec sheet says it can transmit and receive data from up to 6 miles. Also, it operates on low power, which is ideal since we didn't want to drain our battery while using this project. It also runs on the Zigbee standard, and the Zigbee standard is a standard for wireless communication, like low power wireless communication. And also we've had previous experience with the XCTU software that is used to program these boards. We got experience in a previous course.
Now right from the start, the XB radios don't automatically communicate with each other. There is some programming and changes that you have to make to each board. What you're seeing on the right, this is a clip from the XCTU programming software, and this allows you to change the parameters and different aspects that each radio can be programmed with. The first thing you'll see here is the device type. This basically sets it if it's a coordinator or if it's an end node. In this case, you're looking at an end node here, so this coordinator enable switch is not turned on to be a coordinator. Next, this is the current address of the device. So every device has an address, kind of like your house where you get mail sent to. So if something were to be sent specifically to this device, to this end node, you would need to use the address that is provided right there, and it will send data directly to it. This is kind of the opposite of that. It's the device, the destination. So in this case, since this is an end node, our destination address is set up to the coordinator's address. This means that when a transmission is sent, it will go directly to this address, which is connected to the coordinator, and the information will be sent that way. And lastly, this is an identifying marker for each node. You can set this to be whatever you'd like, but this is just an identifier to let the coordinator decipher which node is currently transmitting and it's receiving data from. So when we first started designing, we had all these parts, a GPS, accelerometer, and all of that, but we needed to find a good way to put everything down together. We knew we were going to have to withstand vibrations and be sturdy since it's going to be out in the field and being bounced around. So we decided to make a 3D model of our shield to make sure that we would be able to have everything fit and have good clearance, and there would be no issues when we first made the board. So as you can see on the left, this is just a 3-dimensional model. If we were to have this model printed, everything would be within 0.003 inches. This is due to using a very, very accurate micrometer to measure all the components and locations of where we were going to place them. Unfortunately, we can't get that much accuracy with the Eagle, which is the software that we used. So we got it to be roughly within 0.02 inches based on the annotated schematic that you can see here. Basically just places all of the parts and shows all the locations for where we decided to put things, which translated really nicely when we actually made the board. This is the schematic. So this is pretty much just laid on that board. You can't see it in the 3-dimensional view, but we had created this so that way we could use our board layout. Each device itself had a row of pins to be inserted, and that's how it would connect to the circuit and the board, like the accelerometer, the GPS, and so forth. And that was then all connected to the pins on our shield, which is the Arduino in the middle. It's actually just the shield that lays on top. All of that then translated into this board here. As you can see, the blue traces are actually on the bottom of the board, the red traces are on the top. And this is where our step-up converter went to run our amplifier. This is the accelerometer, the thermocouple amplifier, GPS, thermocouple connection, and then this is where we would plug in the XP radio so that it could communicate with the Arduino board. And based on our three-dimensional model, all of our parts fit perfectly. There were no clearancing issues, there was no tolerancing that took place that we had to change or anything of that sort. So the 3D model definitely aided in that. And this is the final design. As you can see, all of our parts are placed as they were, and everything is ready to go.
For the firmware, I wrote an Arduino sketch, and the sketch was for the most part was configuring the GPS, and a timer interrupt was called every 1 millisecond to look for new GPS data. Once the GPS actually got a fix, the data would be stored in a character. Simultaneously, while this was happening, it would read the voltage and temperature data, read voltage and temperature data, and it also read the accelerometer data. And this right here is the interrupt, a snip of the code of the interrupt for the GPS. Right here is reading the value from the thermocouple and also the accelerometer. And then once it's serially transmitted the data, that snippet to the left shows all of our serial transmits along with characters to be used in application. For example, before the temperature, a T would be printed, and then the actual temperature printed. So when Eric used it in his application, he'd know the next set of data was the temperature.
So this is basically our constructed end node. Previously you saw the board just by itself connected to an Arduino board. But this is it within our box here. The box we used was an ABS polycarbonate, which allowed it to withstand all the temperatures that we had set forth in our requirements. And the box, I don't know if you can see, there's a ridge, Matt can probably point to it, a ridge around the top of the box, up a little right up here. Yeah. And that goes into a rubber seal, which then completely makes the interior of the box watertight. And you can see little gaps near each screw hole. Those we actually decided to use for the temperature sensor, so that way it would not be stuck in the box and be able to read accurately. By putting the temperature sensor in there, it limited the chances of water or anything getting into the device and ruining all the electronic components in there, but it allowed the temperature sensor to be outside, so that way it would be able to get accurate temperature readings.
And for the software, since everything was being transmitted serially, I would read in this data through the serial port on the computer, and the data from each node came in one packet, so I would parse through that packet using, as Matt said before, the T to determine which was the temperature value. So I would get the accelerometer data, temperature data, and GPS data from those packets. And these packets would be read in every half a second. And then there's conversions done where necessary within the application to graphically display the data for the user. And here is a screenshot from the application running. As you can see on the top, there's a selection tab. The overview tab is just a basic overview description of the software. And within this individual tab, you can select from the drop-down menu in the top left corner which firefighter you want to view. And with the selected firefighter, you can see their current and max temperatures, and also a plot of their temperature over time. And then if you go to the temperature tab, you can see an overview of all the firefighters that have devices connected to the application, and you can see their current and max temperatures. And as you can see, there's a different color scheme being used for temperatures. We had it so blue temperatures were relatively cool, orange were medium temperatures, and red for hot temperatures. This will allow for the user of the application to better see which firefighter is in the location with the hottest temperature and focus more attention there. Then if we go to the Maps tab, this was us testing it prior to checkoff around the Pentacrest, and you can see the location of each firefighter is displayed on the left, and then a pin is plotted on Google Maps for each firefighter. And to make it easier for the user of the application, you can go to the settings and change the name of each firefighter. In this case, it was Matt and Brian walking around, so then you know which pin matches up with which actual firefighter. And then you can also change the view type for the mat. So instead of just the road mat view, you could change to a hybrid view so you could still see the roads and also see the terrain surrounding the firefighters at that location.